This example problem is what I call an isomer matching problem. On the left, we have 5 pairs of molecules. You're asked to define the relationship between each pair. The relationships are listed in the top right corner of the page. You will use one relationship only once. You will never use any relationship more than once. So you can use process of elimination to your advantage. In the box, I've written what I call my process of doing this problem. There are 4 questions that you can ask that will help you determine the relationship of each pair. These questions are based on the definitions of each kind of isomer. For example, an isomer in general has the same molecular formula, although it is not the same molecule. So to determine whether each of these pairs is related at all, we should first find the molecular formula for each molecule. In number 1, our first molecule has 2 carbons. So if we write its molecular formula, it is C2. It has 2 chlorines. It has a hydrogen and a bromine. If we look at our second molecule, it has the exact same molecular formula. So the pair of molecules at the top are related in some way, so we haven't found our not related molecules yet. If we look at the first molecule in pair number 2, it also has 2 carbons, 2 chlorines, a hydrogen, and a bromine. And if we look at the second molecule, it's exactly the same as the one above it, so it has the same molecular formula. So far, pairs 1 and 2 are some kind of isomer. If we move on to 3, this one has 2 carbons. It has 2 chlorines. It has a bromine. And if we count, there's a hydrogen that's shown, and then on the second carbon, there are 2 hydrogens that aren't shown. If we look at the second molecule in this pair, it also has 2 carbons, 2 chlorines, a bromine, 1 hydrogen on the carbon on the left, and 2 hydrogens on the carbon on the right that aren't shown. So we still haven't found our not related molecule. So let's move on to pair number 4. This first one has 2 carbons. It has 2 chlorines. It has a hydrogen and a bromine. If we look at the second one, it has 2 carbons. It has 2 chlorines. It has a bromine. But if we look, there's no double bond in the middle. So there is a hydrogen that's shown, but then there is also a hydrogen on each carbon that wasn't shown. That was kind of sneaky of me to do. I made them look similar by leaving out 2 of the hydrogens and only showing 1 of them. It's perfectly allowed to do because for the skeletal structure, you can leave hydrogens in or you can take them all out. Sometimes I leave hydrogens in to emphasize them. In this case, it just makes them look the same. But you can see that the molecule in pair 4 on the right had 2 more hydrogens than the one on the left. So if you just take a cursory look at the molecules themselves, you can see that one has a double bond and the one on the right does not. So this is our pair of not related molecules. They are not related because they have a different number of hydrogens. So we have one choice down. And we asked 1 question, same molecular formula. So we're done with that question. The next question we should ask is, do the molecules have the same connectivity? And we don't need to pay attention to pair number 4 anymore because we've determined their relationship. So we only have to look at the remaining 4 pairs. Starting back again with the first one, we can see that we have 2 carbons with a double bond between them. We have a chlorine on the carbon on the left and a second chlorine on the carbon on the left. If we look at the second molecule in pair number 1, the first carbon has a chlorine and a bromine. That right away, without any further inspection, makes them have different connectivity. We have actually found our structural isomers already. But just to be thorough, let's look at pair number 2. Pair number 2 has a double bond between two carbons. On the first carbon is a chlorine and a bromine. On the second carbon is a chlorine and hydrogen. The second molecule in that pair has the same connectivity. The second carbon, however, has the hydrogen going up instead of down. If we look at number 3, we have two carbons in the middle. The first carbon has a chlorine, a hydrogen, and a bromine on it. The second carbon has a chlorine and two hydrogens. The second molecule in this pair has the same atoms attached to these two carbons. If we look at number 5, we can see that, again, the connectivity is the same. The first carbon has two chlorines in both. The second carbon has a hydrogen and a bromine on it. So we have indeed correctly identified pair number 1 as our structural isomers. And by the way, structural isomers are also known as constitutional isomers. Constitution being a synonym for connectivity. In my opinion, the next easiest pair to identify is identical. So we've already asked the question, do they have the same connectivity? The next question we ask is, are the molecules superimposable? Superimposable means, can you take the molecule as it is drawn, pick it up, and plop it down on the other molecule and make everything match up to be identical? In other words, can you redraw the molecule by only flipping it over or rotating the entire molecule to make it look exactly the same as the other one? We'll skip pair number 1 because we've already identified it. If we look at number 2, if we try to pick number 2, the first molecule in number 2 up and put it on top of the second molecule, the hydrogen and the chlorine will not match up. So those are not superimposable. If we do the same thing with pair number 3 and try to make the two molecules match up or superimpose, we get everything attached to the first carbon to match up. But if we look at the chlorine on the second carbon, it's up in the first one and it's down in the second one. They will not be superimposable without doing some kind of rotation, which if they're identical, you cannot do. If we look at number 5, if we try to pick up the first molecule and put it on top of the second molecule, you can see that the hydrogen and the bromine will not match up. But if we take that molecule and if we do what I call a pancake flip with it and flip it over in such a way that the entire molecule is flipped over, because it's flat, the chlorines will match up. The bromine is now on the top and the hydrogen's on the bottom side of the molecule, and everything will match up. So notice I didn't do any rotation. My little arrow is indicating that we're taking the entire molecule, scooping it up like we're scooping up a pancake, and flipping it over. Because we've done that without rotating any bonds, without breaking any bonds, these molecules are superimposable, which means we have found our pair of identical molecules. So we found them. We asked the question if they're superimposable, and we found the pair that are. The next question is in order to identify conformers. Conformers are identical molecules that are only different by rotation around single bonds. Remember that you cannot rotate around double bonds because you would break the bond. We only have two choices left. If we look at number 2, at first glance it looks like we could rotate around the middle bond to get the hydrogen and the chlorine to match up, but that's a double bond, so we cannot do that without breaking the bond. If we look at pair number 3, if we rotate around the carbon-carbon bond so that the chlorine moves so that it is down, we do get the same molecule. So choice number 3 is our pair of conformers. So we have found those. We have asked the question superimposable after rotation. The only remaining choice is stereoisomers. Stereoisomers have the exact same connectivity, and we determined that already. We have a carbon-carbon double bond with a chlorine on the first and a bromine on the first, and then a chlorine and a hydrogen on the second. You can see, though, that the atoms are not arranged in the same three-dimensional space. If we look at the second carbon, the chlorine in the first molecule is on the top. If you look at the second molecule, the chlorine on the second carbon is going down. You cannot rotate to make them the same. There's nothing you can do to flip the molecule over or rotate it around to make it be superimposable. So these are stereoisomers. They are same connectivity, so the same atoms are attached to our double bonded carbons, but they're not arranged in the same space. Another way to tell if two molecules are stereoisomers is to take the full structural or the line structural formula that shows the three dimensions and put it into a condensed formula. If they're stereoisomers, the condensed formula should be identical. If we do that with these two molecules, we have a carbon with a bromine and a chlorine attached to it, and a carbon with a hydrogen and a chlorine attached to it. That's for the first molecule, but you can see if we did that for the second molecule, it would be the exact same. Another thing I say is to imagine squashing the molecules flat and showing no three-dimensional, only two-dimensional aspects of it, and they should be the same. So hopefully that was helpful. You may want to watch another example in another video.